So now we are going to go for low IF receivers. So considering all the properties of different types of receivers, whatever we have seen zero IF, we have seen heterodyne, we have seen double heterodyne, we have seen image reject architecture. So now we are going to go for low IF receivers. So low IF receivers, we are going to go just to ensure image rejection. So the image will fall in the band, but it's suppressed by image rejection operation. So low IF means the IF will be very close to your RF. So that will ensure image will be there in your system, but by using appropriate signal cancellation techniques, will ensure that this image rejection is going to happen. So consider we have a 200 kilohertz channel, so which is 0 IF may be corrupted by 1 by F noise. You have an antenna, right? So whenever you have an antenna will pick up noise just like that. So all the received signals and the noise will be presented to the receiver. The antenna will pick up the noise from the signal from the free space. So apart from get tuning to the desired frequency, the antenna will pick up the noise also. So furthermore, so when you are going to have that noise and DC signal getting added to your receiver, so filtering may not be an desired solution. Okay, so filtering may not be a desired solution. So if the yellow frequency is placed at the edge of the 200 kilohertz channel, so RF signal, when you translate RF to IF, you will have frequency difference of just 100 kilohertz. So I'm going to have an LO, which is going to be very, very close to my channel. So that will ensure that the difference is minimum and the IF frequency is going to be as small as possible. So when you have such a low IF, the noise, 1 by F noise will not interfere with your system that effectively. 1 by F, as the frequency is going to be larger, the noise is going to be less. So when you see in frequency domain, but here we are going to have the frequency of LO very close to your RF signal, so that I'm going to eliminate this 1 by F noise in the receiver. Also, when the frequency of operation is very less, I can fabricate it very easily, and the chip can be easily designed to have these types of receivers. So that is going to help me in the fabrication also. See here, this is the message signal. It is going to have bandwidth of 200K. Assume that FLO is somewhere at the edge of your F3. So when you mix these two signals, you get one signal centered at 100K and one signal centered at minus 100K. So when you do the adjacent channel, there will be a decent power level of 9 dB difference, which will ensure that the interferer is 9 dB more than your essential signal. So I need to ensure that I'm going to filter only my required signal and I'm going to reject my interferer completely. So that is this example specific to a GSM channel. Okay. And this heterodyne will have an issue of the image, and image will be very close to your channel. As we seen in the figure, in this architecture, I will not say image will be completely removed, but image will be there, but image will be very close to your channel. So filtering has to be done perfectly. For GSM, you see that this channel is only 9 dB above the desired channel. And if you are going to have an IRR of 30 dB, the image signal remains 21 dB below the signal. So if this thing is going to implement an IRR architecture, we have seen that if IRR is 30 dB, it means that the image is 30 dB less than your noise. So here, if you assume the 9 dB is your channel power, so the image will be 21 dB below your channel. So how is image rejection possible in low IF receiver? So I am again going for Hartley architecture only, because in Hartley architecture we have seen by employing a proper RC and CR network, I can eliminate the noise